What is going on, everyone? Welcome back to another ANSYS tutorial. Today we're back in Fluent simulating Couette Flow, and I'll show you how to do it. So just a quick overview of Couette Flow before we start. Couette Flow is a shear-driven fluid motion that describes the flow between two infinitely long parallel plates that are separated by some small distance h, where the upper plate is moving with some velocity u, and the lower plate is stationary, meaning that the velocity is 0. As we can see by the graphic in the middle here, our velocity profile of Couette Flow can be described by a linear relationship. This linear relationship can be derived from the Navier-Stokes equation. By taking a simplified version of the Navier-Stokes equation, neglecting pressure gradients, we also have two boundary conditions, which are based on a no-slip condition for viscous fluids, which describes that the fluid at a solid boundary will have the same velocity as that boundary. How does this apply to Couette Flow? Well, our bottom plate is a stationary plate, so our boundary condition at this position, we know that the velocity will be equal to 0. Furthermore, we know that the top plate is moving with some velocity u. Therefore, we know the fluid that is at some distance h from our stationary plate will have the same velocity as the moving plate. By integrating twice, we obtain the linear relationship for our velocity profile as such. Therefore, when simulating Couette Flow in ANSYS Fluent, we expect to obtain a linear relationship between the velocity and the distance between the two plates. For this simulation, we are going to be analyzing the flow of water between two parallel plates. The plates are going to be separated by 5 millimeters, and the upper plate is going to be translated with a velocity of 0.02 meters per second. And of course, the lower plate is going to be stationary. And as you can see by the graphic here, this is the result that we will obtain through ANSYS Fluent by preparing this simulation model. All that being said, let's jump right into it. So now with Workbench open, we can go ahead and start our simulation. First thing that we're going to do is drag the fluid flow analysis system into our project schematic and double click on geometry to launch SpaceClaim. Now with SpaceClaim open, we can go ahead and build our geometry. For CFD simulations, what we want to build as our geometry is the fluid domain, or wherever there would be fluid within our system that we're analyzing. And this is different from FEA simulations where the geometry that you CAD is actually the object itself. So let's go ahead and build the geometry. First thing that we're going to do is end sketch editing over here. The reason is because by default, ANSYS has us sketching on the ZX plane, but it's always better for 2D simulations to sketch on the XY plane. So I'm going to go ahead and end that. And I'm going to re-enter sketch mode by pressing on sketch mode. And I'm going to choose the XY plane here. I'm going to make this planar to the screen, so it's flat. I'm going to take our rectangle command up here, plop it at the origin, drag it out. And we're going to dimension the width to be 5 millimeters, like so. And our length is going to be 100. Now with our sketch completed, we can go ahead and press on End Sketch Editing, or you can press on the green prism down here to return into 3D mode. And this is actually going to build our surface. As you can see here, now we have a surface. And for this simulation, that is how simple our geometry is going to be. So now that our geometry is built, we can go ahead and start the meshing. So we'll exit out of SpaceClaim, go back to Workbench, and double click on mesh here. And as you can see, starting up mesh in the bottom corner. So we'll wait for that to load. So now with the mesher loaded, we can see our geometry here in the console window. Let's make this planar to the screen so it's all flat. The first thing that we're going to do is create the default mesh. So in order to do that, we're going to right click on mesh and press on generate mesh. And by doing this, ANSYS is going to automatically create a mesh for us. Now, as you can see, the mesh that it created is fairly coarse. If we go ahead and press on the statistics down here, we can see that we only have 20 elements within our mesh, and the width only comprises of one element. So it's going to be necessary to add some refinements in order to make a much finer mesh. In order to do this, we're going to right click on mesh, and we're going to insert a sizing. As you can see down here, the yellow boxes are the information that ANSYS needs in order to create the new sizing of our mesh. So it needs a geometry scope, and it also needs to know how we're going to define the type of element, whether it be element size, whether it be number of divisions along a certain face, so on and so forth. So what we're going to do is we're going to press on the edge, the face selector tool, up here, and we're going to choose our face, which is the whole fluid domain. And we're going to apply that to our sizing. And for the element size, we're going to put a size of 0.0005 meters. So now with all of our information put into place for the sizing, we can go ahead and update our mesh. Right click on mesh and press on update. As you can see, our new finer mesh has been created. And for such a simple simulation like the one that we're doing, this mesh will be more than okay to get an accurate result. The next thing that we have to do in the mesher stage is create our name selections. And this is very important because it allows Fluent later on to know where to apply the boundary conditions, such as the inlet, the outlet, and the walls. So in order to do our name selections, we're going to go ahead and press on our edge selector tool, and we'll get the first edge over here. Right click and press on create name selection. This is going to be the inlet of our fluid domain. And we'll choose our other edge over here and name this the outlet. Finally, we have our two walls, our stationary wall and our moving wall. So it's important that we don't group these walls in the same name selection because they're going to be moving at different velocities. So we'll choose our bottom wall here, right click, press on name selection, and we'll name this stationary wall. And we'll select our top edge up here, create a name selection, and call this moving wall. So now we go ahead and press on name selections, press on the plus. We can see all of our name selections, and we can verify if we put them in the right place. We have our inlet on the left wall over here. We have the outlet on the right edge over there. We have our stationary wall on the bottom and our moving wall on the top. So now with our mesh created and our name selections in place, we can go ahead and start the actual setup in Fluent. So we'll go ahead and exit the mesher. Go back to the workbench. And as you can see, there is a lightning bolt beside mesh. So this means not all of the information was sent from the mesher to the setup of the program. So in order to fix this, we'll go ahead and right click on mesh and we'll press on update. So what this is going to do is it's going to send all of the information that we created in the mesher stage and put it into the setup. And generally this happens because we've created our mesh, and our mesh automatically usually gets sent to the setup program, but the name selections do not. So oftentimes when you create your name selections last, you'll often have to update this section in the workbench. And as you can see, we now have a check mark, meaning all the information from mesh has been sent to the setup. To launch Fluent, we'll go ahead and double click on setup. As you can see, we're met with the Fluent launcher, and there's a couple things that we need to specify before actually launching Fluent. The first one would be the dimension, but as you can see, it's grayed out because ANSYS already knows that we've used a surface for our geometry, so it knows it's going to be a 2D simulation. The next thing that we're going to want to do is press the check mark here to get double precision for our simulation. And lastly, and this is specific to your personal computer or whatever you're running ANSYS on, is the solver processes and solver GPUs. I know on my personal machine that I have 2 solver processes and 1 GPU. But this, again, is dependent on whatever you're running ANSYS on. So with all of this information in place, we can go ahead and start Fluent by pressing on the Start button down here. Now with Fluent Launch, we can go ahead and start the setup of our simulation. All the general setup is going to be left the same here. We have pressure-based, steady, absolute, and planar. So that is good. For models, what we're going to want to do is change viscous here to viscous laminar. So if you double click on viscous, it will open up this window and we can select laminar from the model and press OK. The next thing that we're going to do is define the material that we want to use for our fluid, whether that be water, air, so on and so forth. So in order to do this, we can go ahead and press on the plus here beside material and press on the plus beside fluid. And you can see by default, ANSYS has air being run for our simulation, but I want to use water instead. So I'll go ahead and double click on air. And this is going to open up create and edit materials. And if we press on Fluent database, we get our whole list of Fluent materials that is accessible in ANSYS. So if we scroll down all the way to the bottom, we can go ahead and find water liquid, which will open up all the properties that are included by default in ANSYS. And if we wanted, we could go ahead and change these values if you had specific values you wanted to solve for. So to add water to our simulation, we can go ahead and press on copy and we'll close this window. And as you can see, water liquid has been added to a fluid material in our tree here. And we'll close this window as well. However, just because we added liquid water as a material, it doesn't mean that this is what is being initialized as our fluid domain. So if we go ahead and press on cell zone conditions here and press on the surface, being the surface of our fluid domain that we catted, we see that the material is still air. And if we go ahead and press on the tree here, we can actually change this to water since we added water to our material tree. Now, no matter how many materials we added to this tree, all of them would appear here, and you need to select here in the cell zone conditions what material you want to use. So for the simulation, I'm going to use water. So I'll go ahead and press on water, and I'll press apply. And I'll close this. So now water is being used as our material of choice for our fluid. The next thing that we're going to do is check the boundary conditions. So we'll go ahead and press on the plus beside boundary conditions. Actually, we'll double click on boundary conditions. Sorry, it'll open up the task page for boundary conditions. And we can go ahead and press on inlet. We see that this is a velocity inlet. So that is not good for us for this Couette flow. What we're going to want to do is change this to a pressure inlet right here. Very good. We can close this. We have our outlet. Oh, I didn't mean to double click on that. Is our pressure outlet. So that is good. We have our stationary wall, which is specified as a wall. So that is good to go as well. And we have our moving wall, which is also specified as wall, which is good. However, we need to now initialize a magnitude for the velocity of this moving wall, because by default, it's going to be 0. So if we press on stationary wall here and we go to edit, it'll open up this window. And as you can see, we have stationary wall by default. So if we close that and we go to moving wall instead and we press on edit, we need to make sure for Couette flow that we actually make the moving wall a moving wall, because right now it's a stationary wall. So we'll press on moving wall and it will open up this window here. And we'll give it a velocity of 0.02 meters per second, which will give us a Renaud's number for the simulation of 100. Knowing that obviously Renaud's number is a rho VD over mu, where rho in this case was given by ANSYS to be a constant at 998.2. We know that the thickness D of our CAD is 5 millimeters because we are the one that inputted that measurement. And we know that mu, the viscosity of the fluid, was given again as a constant for water in ANSYS of 0.001003. We also have the direction of the moving wall to be in the X direction. This is why before I counted on the XY plane, I know now that my X direction is going to be the length of our model, of our geometry. So I know that to apply the speed of this wall in the X direction. So that is good to go. So we can go ahead and press apply, and we'll close this window. So now all of our boundary conditions have been set up. We can go ahead and move on to reference values. And we're going to compute the reference values from the inlet. So that is good to go. As you can see, it changes the density and the viscosity to the constants that are included for water liquid. Now with our reference values in place, we can go ahead and initialize our simulation. So we'll go ahead and press on initialization. And we'll choose hybrid initialization and press on initialize. As you can see down in the console window, it says hybrid initialization is done. So that is good to go. You can also see that I got a warning that says convergence tolerance of 1 to the -6 not reached during hybrid initialization. Now, reaching convergence during your initialization is not too important. It's a warning that can be ignored as we continue on with this simulation. If convergence was not reached during the actual computational analysis and calculations of when we're running our simulation, that would be a little more problemsome. However, if you do want to fix this warning, it's very easy to do. You can go ahead and right click on initialize, go to more settings, and up the number of iterations here to give the hybrid initialization enough attempts to reach a convergence. And now we can go ahead and run our calculation. So we'll double click on run calculation. Now, the information that we need to provide ANSYS before we actually run our calculation is the number of iterations that we want to perform. And for this simulation, I'm going to put 1,000 iterations. So that is good to go. So now we can go ahead and press on calculate. And as you can see in our console, it's starting to write out the calculations. And all of our plots that we would, and all of our monitors are opening now in this view window here. So as you can see, it's now calculating the scaled residuals. Now, if we had other monitors, say if we were calculating lift and drag, and we printed these monitors to the screen, it would go ahead and be printing. It would open 2 other tabs or 3 or however many monitors you have, and it would print the results in real time like it's doing for these residuals. So this is going to take a bit of time to do the calculation. So I'll go ahead and cut until when we're back. Now with our calculation complete, we can go ahead and move on to our post-processing and view our results. So press OK. We'll close Fluent. Oh, press OK. You'll start its closing results. And we can double click on results here to open CFD post. Now with CFD post open, we can go ahead and view our results. I'm going to press on the Z here to make it flat to the screen. The first thing that we're going to do is add streamlines to our results. To do this, we're going to press on the little airfoil icon up here. Press on OK. Most of the details of this streamline are complete. The one thing that we need to specify is where we're going to start our streamlines from. So we're going to choose the inlet in this list. And what we can also do is up the number of points here from 25. So what this is going to do is if we add more points here, we're going to have more streamlines. So we can go ahead and double the amount of streamlines if we were to put 50. And the variable that we're going to be looking at is the velocity. So that's all good to go. We can go ahead and press on apply. And here we have our streamline velocity profile for our Couette Flow. As we can see at the top over here, where the moving plate occurs, we have the velocity of 0.02, which we applied. And at the bottom here, we have our stationary wall, which has a velocity of 0. So that is a fairly good result. Now let's create the animation. So in order to do this, we'll go ahead and press on the film icon up here. The type of animation we're going to create is the sweep animation. We're going to choose our streamline to be the object that we animate. We can adjust the speed of the animation by dragging this dial here to either side. So I'll leave it in the middle. Now for the animation, it can either be a bounce animation or a loop animation. Bounce animation, what's going to happen is once the particles reach the end of your geometry, they're going to bounce and head back in the direction that they came. Now, this is not very descriptive for us because our flow is going in one direction. So what we're going to do instead is we're going to press on the loop here so that when the particles reach the end of our geometry, they're going to reappear at the beginning and loop back and retrace the path that they did. For the number of repeats, I'm going to choose 5. And in order to save the movie, you need to put a check mark beside save movie. This is the location at which it's going to be saved at, and you can change the location by pressing the folder here. And FFF in this file location marks the file name that it's going to save the animation in. So if you wanted to change the name of your file, you go ahead and change the FFF here. So I'll rename this to Couette Flow. And Windows Media Video is good to go. If we go ahead and press on options, we can see a lot more parameters that we can adjust here. We can determine the spacing that we want our symbols to be. We'll leave it to 0.6. We can choose a symbol size. Now, since our geometry is fairly small, this symbol size is going to be quite big on the geometry. So I'm just going to go ahead and decrease this a little bit, not too much. And you can also choose the symbol that you want. So we're going to leave it to ball, and you'll see what that means in a second when we go ahead and run the animation. But you can choose all of these different kinds of symbols. For the image size, we're going to go ahead and choose HD Video 180p. And in advanced settings, make sure that your quality is the highest it can be to get the best video. So that is all good to go. Now, in order to start running the animation and start saving it to your computer, you go ahead and press on the play sign here. As you can see, our animation is starting to be run here. These are the balls that are being traced along the streamlines that we've created. And down here, we can see there's a progress bar showing us the progress of the animation being saved. So I'll wait for that to complete, and then I'll show you guys the completed animation in the next cut. Welcome back, guys. As you can see, this is the animation that was created by post-processing in ANSYS, and it was saved as a file somewhere on our computer, and it just opened up in a simple video viewing format. And in this animation, we can see that our particles are being traced along their respective streamlines. The particles near the top or closer to the moving plate move with a much higher velocity since this plate is moving. And as we go down towards the stationary plate, the particles start moving slower and slower. So this is a fairly good result, and this is what we expected to see through the Couette Flow. So now that we're back in CFD post, the next thing that we might be interested in doing is creating the graph in order to see the velocity as a function of the thickness between the two plates. And for ideal Couette Flow, we expect this to be a linear relationship. So it's good to have an expectation for what our results are going to look like in order to validate them. So in order to create this graph, the first thing that we're going to do is put a line somewhere along our geometry of where we want to take that relationship at. So what do I mean by this? Well, if we go to location and we insert a line, call this line 1, and say we define a line in the middle of our geometry, this will give us the relationship between the velocity and the thickness at this location. Now, if we were to do it maybe farther up ahead, you can see that the flow is developing into something at the beginning here. So this result will be different than it will be if we take it at the middle or at the end. So depending on where you want to define your relationship, this is where you would go ahead and define your line. So in order to define a line, what we do is we define 2 points here. The first number being our x coordinate, second one being our y coordinate, and third being our z coordinate. Now we know that our length here is 100 millimeters. Now this will automatically take it in meters. So we got to go ahead and change this to meters. And we're going to divide by 2 in order to get it into the middle of our geometry. Now for the y coordinate, we know that we made the thickness 5 millimeters, and we know that we created the bottom corner at the origin of the CAD. So we know for the y coordinate on the bottom surface here, it's going to be 0. And we know that the next point to create a straight line upwards will be 5 millimeters up here, or in other words, 0.005. And evidently for the z coordinate, we leave it to 0 because this is a 2D line. So once you have your coordinates in place, you can go ahead and press apply. And as you can see, if we remove the streamlines here, you can see that our line has been created in the middle of our geometry. So now we can go ahead and plot our relationship of the velocity versus the thickness at this location. So in order to do that, we'll go ahead and press on the graph symbol up here. You can name the chart whatever you want it to be. The title of our chart will rename to Couette Flow. For the x-axis, we're going to choose our variable to be the velocity in the u direction. And for our y-axis, we're going to choose our variable to be the thickness between the 2 plates, or the location along the 2 plates. Now, in order to choose the location or the line that we created before, we go ahead and press on data series. And where it says data source location, we go ahead and press line 1. So now it's going to plot the relationship of velocity versus thickness in the middle of our geometry. So if we go ahead and press apply, we can see that this is the linear relationship that we expected to get between the velocity and the location between the 2 plates for our ideal Couette flow. The velocity is 0 at the stationary plate or at the bottom of our geometry. And as we move closer to the moving plate, we can see that our velocity is increasing linearly until it reaches the velocity of the moving plate at 0.02 meters per second. So this is a good result. You could also save this graph if you wanted to as a file somewhere on your computer like we did for the animation. In order to do this, you would go ahead and press on File over here, and you would choose the location using this folder here and press on Export. And that pretty much sums up how to model a Couette flow in ANSYS Fluent. Don't forget to give the video a like if you guys thought it was helpful, and subscribe for more engineering content.